some theoretical aspect mixed with some flex motor aspect. People who already followed the training on design of build DC motor theory and flex motor aspects, we are going to see the same chapters, mainly for basic laws, as well on materials and winding. But there are a few chapters in these theory aspects that are more specific for synchronous reluctance machine. Yeah, so this is about the learning path we have. We have two learning paths in parallel that can be grouped at the end for the most advanced training or more advanced users for rotating machines. For our training today, it will be really good if you have already followed the introduction training within flex motor. So you will have or you have already the philosophy behind, and I hope that you have already started some analysis with flex motor. Then, yeah, so this training we are going to see some theoretical aspects. Maybe you know them already, so we are going to remember them together, and then we will see the link between this theory and flex motor, and how to use flex motor at the end of this session, how to use flex motor to pre-design a synchronous reluctance machine. Yep. So today we are going to see two modules, basic laws and getting started with flex motor and some principles there. These two modules are actually in one session, not in two sessions, two separate sessions, sorry. And the last session, we are going to design together or make an example to design together a synchronous reluctance motor from some specification. I have already sent you the material training today. I hope you have already received it. Okay. And I am going to use material training a little bit different from the one you have, just because it is more practical for me to have one slide and where I group all the information, but the same information are available in your the material training I sent. Yeah, so I'm going to start from one module, and then we'll have like 10 minutes of break, and then we come back to the second module. At the end of this module, we will have some minutes to question and answer. If you have questions, I will be happy to answer them. And yeah, let's start. Okay, so then what we are going to see today is to try to understand the phenomenon behind rotating machine. All what we are going to see is linked for rotating machine. So as the story start from magnetic field, because rotating machine is an interaction between two magnetic fields, one on the stator and one on the rotor. So let's see what is this magnetic field. Yeah, the magnetic field on the stator is created by the winding. So the winding is actually electric cable that we supply. So when we supply an electric cable, we are going to create a magnetic field. Yeah. So then this magnetic field will be surrounding the cable and expressed by mathematical equation, which is the rotational of H equal to G. G is the current density. Yeah. So then this is what happens on the winding, and the interest of that is in the winding we will try to create a magnetic field, rotating magnetic field. This is the what we are going why we are using winding in the stator, and we are going to understand how to create that rotating magnetic field. Yeah, so this is the first law, or rotational of H equal to G. So once you supply the cable, you have the creation of the magnetic field. And there is another phenomena, which is back EMF, right? So like your dynamo, when you move the rotor, you recover like a voltage on the stator, and you use light there, and it would be shining. So we produce electricity. So when there is magnetic field variation, then we are going to create voltage. Here is, for instance, we can have this magnet in front of a coil or turn. And then if we move this magnet, we are going to create magnetic field variation. Then on the coil, we are going to see a voltage. Once again, this is the same principle on the dynamo. If I supply this coil and I rotate it, I will recover voltage here. So when there is a magnetic field variation, there is a voltage creation, and this is expressed by Faraday's law, or the most known one is E equal to minus dphi by dt. So the magnetic flux variation across the time. So minus is just to say that it's opposite to the source of the magnetic field creation. So this is an important second law phenomenon that we need to know for rotating machine. The third one is really important because if you have a magnet, the magnetic field created on the north is the same quantity of the magnetic field going to the south. And if you have electromagnet or a coil, and you produce like a magnetic field north and south, the magnetic field created from the north, the quantity is recovered, the same quantity is recovered by the south. So it's always like this. We cannot produce like 100% of the magnetic field here and recover only 30%. This is something we cannot do, and it's not physical actually. Then the magnetic field creation and variation is something that we need to canalize this magnetic field. And this is why we use steel or magnetic circuit on the, and we are not using plastic or wood on the stator or the rotor. Yeah, so then why? Because we need to canalize it. So when we talk about materials, then when we talk about canalize the magnetic field, then there is one term we have to know, which is the magnetic flux density. So this magnetic flux density is depending on the quantity of the magnetic field or flux on a given surface, and it's linked to the characteristics of the material. Yeah, so the magnet itself is a material and it's the source of the magnetic field as well. So then this is really specific things because it has in the same time some material characteristics, and it is the source of the magnetic field. Then in the magnet, we are going to see G, the magnetization of the magnet, plus mu0 multiplied by H. This is the magnetic field. It can be external magnetic field actually, and this is the sum of both the magnetization and the mu0 multiplied by the magnetic field is equal to B, right? So B is the flux density. If we are not talking about magnet, then we are talking only about material. So a material is always characterized by this B equal to mu multiplied by H. H is again magnetic field, B the flux density, and mu is magnetic permeability. Yep. So the magnetic permeability is a product between the vacuum permeability and the relative permeability of the material. So as you can understand, if you are in the air, the permeability mu is equal to the vacuum permeability. The aluminum, for instance, is or the copper has the mu air equal to 1. So from magnetic point of view, the aluminum or the copper behave as air or vacuum. That's why we are not using aluminum or copper as stator lamination or rotor lamination, because it will behave as air or vacuum, and we are not going to canalize the magnetic field. Yeah, so then if we talk about the magnetic material, then we are going to see this mu air variation. And this mu air variation is actually linked to the magnetic field we apply. Yeah, so then we will see how this it behaves later on, but the characteristics of each material is different actually, and we will see the intrinsic curve, which is the pH curve, the given characteristics of a given material, and you can see that it's saturated. So then when we apply an external magnetic field on this material, we are going to increase the flux density on it. And at a given magnetic field value, we are going to saturate this material. What does it mean? If we plot the relative permeability, we can see that it starts with very big values, and then more you put electric magnetic field on it, more this mu air tends to 1 actually. And 1 is when this mu air tends to 1, so the material will behave as air or vacuum. And we don't want actually to use plastic or aluminum for canalizing magnetic field. So then we need to use this magnetic field for its mu air characteristics, but we don't want to push at the maximum, otherwise it will be like air or vacuum from magnetic point of view. Okay. So then the other characteristics is this diffraction of the magnetic field. It's like the shine actually. When you have when you put magnetic material inside the magnetic field, you will see that there is this kind of behavior. Yeah, this behavior is described by this equation, and as you can see, is really dependent on the relative permeability of the two materials. This characteristic is important because this is what will produce actually later on magnetic energy variation, and then maybe we will talk about torque later, or cooking torque, something like this. And this is something happens in the air gap especially. Okay, so we talked about magnetic field creation, flux density, and the link between the flux density and the permeability and those characteristics. Then we are going to talk about the magnetic flux, because previously we talked about Faraday's law. Here we said that if there is a magnetic flux variation across time, then we are going to recover voltage. So what is this magnetic flux? Yeah, so this magnetic flux is linked to the flux density, given quantity of flux density in a given section. But here, what is interesting to me is to talk more on the magnetic flux conservation. Because once again, when you produce a magnetic flux on the north, you will recover the same thing on the south. There is nothing that will stop this magnetic flux. It can deviate it, but it will not stop it. It will always have this loop closed between the north and the south. Yep, so then this magnetic flux variation, when it moves, yeah, we can canalize it, we can deviate it. And depending on the section offered to this magnetic flux, we'll have given flux density. Yeah, so then if we have the same section like this, then the flux density for the same magnetic flux will have the same thing. If we suppose that there is no leakage magnetic flux, so if we have the same, ideally the same magnetic flux, we will have the same density everywhere. But in this example, where we have the coil and it will produce the magnetic flux, the section here is different from the section here. It is mathematically or mechanically possible to understand that the flux density here will be higher than here. Yeah, and even if we make the air gap, the magnetic flux will continue the movement and move from the north to the south. So there is always this magnetic flux conservation. Yep, I come back again to the coil and the magnetic flux variation. We said that it is when there is a magnetic flux variation across the time, we are going to create the voltage. Yeah, so the voltage, if I come back to it, actually, it's not dphi by dt only, but it's minus n dphi by dt, and n is equal to the number of turns of the coil. Okay, and here the number of turns of the coil is equal to 1. That's why we have this equation. If I come back here, just to understand this aspect. So if I have one coil, and I talk about the magnetic flux seen by this one coil, and this coil has one turn, so the flux on the coil is the flux equal to the flux I produce here. If I have a coil with n turns, the magnetic flux I produce it with a magnet, something like this, I will recover on the coil n phi, magnetic flux I produced, and n is the number of turns. So here, if I vary the magnetic flux, the voltage I am going to have is n dphi minus n dphi by dt. And here, the voltage I am going to have is simply minus dphi by dt if I am going to vary the magnetic flux. Okay. Yeah, so then we start to go more and more on phenomenon that we need to understand the rotating machine. Here we are going to talk about Ampere's law. Why? Because this Ampere's law will help us to build later on what we call magnetomotive force on the coil. So when you supply a coil, you are going to create magnetic field. And this magnetic field created by this coil, it can be really complex because you have three phases and each phase is distributed on the number of turns, right? So we need to compute the shape of this magnetomotive force created by this one phase. And this is done thanks to Ampere's law. So Ampere's law, to make it simpler, the magnetic field created along a path is equal to the number of the sum of the current going inside this path. So these are some examples to understand it more. If I have like this path, circular path, where I have like this coil, so inside this coil, finally you will see the current will enter one time, second time, and third time. So the magnetic field I am going to create on this counter is equal 3 times the current I am going to supply. If I consider the same counter and I want to compute the magnetic field on it, then the magnetic field is equal to 1 time the current entering and 1 time the current going out. So this is an opposition, then the magnetic field is 0. And we can follow like these examples. The interesting one here is the torus. If you have like a torus and then you have n turns around this torus and you want to compute the magnetic field created there. So it's simply NE. So you can imagine that cut that or you put that on the starter of the machine for given phase. Then the magnetic field created by this phase is equal directly to Ni, sorry. Okay. Then from Ampere's law, let's go to Hopkinson law. This is something we are not using nowadays, but really it helps to understand the physics behind. Before numerical methods, this is something we used to use actually to compute electric machines. And numerical method, this is something we stole, if I can say, from mechanic study, because they were the first to use it for mechanical phenomenon analysis. Yeah, so then Hopkinson law will help us to understand a little bit better on the magnetic circuit. And Hopkinson law, there is a link between magnetic circuit and it establishes a link between magnetic circuit and electric circuit. So let's say, consider this small example, a torus, where we have this air gap, right? This torus has like a constant section, S, and the mean length of this torus is L fer. So fer is in French actually, fer is iron, so L iron. and the length of the air gap is E. So on these torus, we are going to wound a coil with a given number of turns N, and we are going to supply it by current I. Right, so then how the link between magnetic circuit or analogy is made by magnetic circuit and electric circuit. So the electric field source is equal to not here, not the small e. It's not the air gap. It's the voltage, if I can say. Its equivalent is equal to Ni. The electric current, its equivalent in magnetic circuit is the magnetic flux. The current density, by analogy, we are going to talk about the magnetic flux density. The conductivity is equivalent to the permeability in magnetic circuit. The resistance is equivalent to the reluctance R, and the conductance is equivalent to the permeance, the inverse of the reluctance. Okay, so we are talking about the reluctance is equivalent to the resistance. So the resistance is rho by L by S, the section. Here we are going, the reluctance is E. This time E is the air gap length divided by mu0 multiplied by S, the section. So here something is not mentioned here. We neglect that there is like a diffraction of the magnetic field. So we consider that there is a direct. I want to say, if I can say like this. So there is now like a leakage or diffraction of the magnetic field when it moves like this. So it's not true actually, because in the reality there is this phenomenon. So if we say that there is a reluctance for the magnetic circuit, there is a reluctance for the air gap. So the reluctance of the air gap is length of the air gap divided by mu0 multiplied by S. Why mu0 in only? Because the mu air of the vacuum is equal to 1. And then here we have the iron, the mean length of the iron divided by mu iron multiplied by the same section. The iron here, mu iron here is mu air multiplied by mu0. And then we have these two reluctance in series. And we have the magnetic field source, which is the coil. And as you remember, we use Ampere's law to compute N multiplied by I. N is the number of turns. So then, what is the limit of this dependency? Here, the flux density or the relative permeability is depending on the flux density and the magnetic field we apply. And the conductivity is not depending on the current we supply on the electric circuit. The current flow and in the component, and we can stop it by the switch. But the magnetic flux cannot be stopped by simply if you put like a air gap, it will continue. If it's an electric current, it will not. It will stop here. So these are the limits of this analogy, and this is something simple actually, because if you apply it on a rotating machine, you are going to have much more complicated magnetic circuit, equivalent circuit. Sorry. So let's move now to the magnetic energy, because all what we say previously and what we are going to do for rotating machine is to canalize this magnetic energy and to maximize it in the air gap in order to maximize the torque. So it's important to know this magnetic energy concept, but it's a really large module, and here I put only few elements. So when you have a given material and you supply it with magnetic field, so you have a winding and you supply it by current and you produce a magnetic field, then there is a magnetic energy stored here. And this is magnetic energy, and actually we are going to see that this is only a part of the curve. And finally, normally we are going to talk about hysteresis cycle, right? So this curve is really what we call intrinsic curve. And the magnetic energy is actually contained inside the hysteresis cycle. So then here is the magnetic energy on the characteristic BH is really the area of this surface, right? Okay, so the magnetic energy, if we develop equation, we are going to see that it's depending on the flux density and the relative permeability, the permeability. And here we can see why we can easily understand why we use air gap in rotating machine, because here mu is mu air multiplied by mu zero. So we said that we can see that the magnetic energy stored in the magnetic circuit is much lower than the magnetic energy we can find in the air gap, because mu air, if it's equal to 1000, so the magnetic energy on the air gap is 1000 higher than the magnetic energy stored on the magnetic circuit. So once again, this is why we use air gap in the rotating machine in order to concentrate actually the magnetic energy on it. So we need this magnetic circuit to canalize and concentrate it uh, directly to the air gap. Yeah, you will hear about virtual work method that use co-energy. Co-energy is uh, has no physical meaning, but it's like the pendant, I don't know how to say it in English, of the magnetic energy, and it uses this co-energy concept to compute magnetic forces. I am going to go talk about magnetic forces later on, but let's first talk about the magnetic energy stored on the magnetic circuit and uh, the magnetic energy stored as well on the air gap. Both of them will be part or responsible of what we call inductance. So the inductance, if you have a coil, and if you supply it by current, you are going to create magnetic flux. Then you are going to create a magnetic energy, and this magnetic energy is directly linked to the inductance, or the inductance that is directly linked to this magnetic energy. And then, so the magnetic energy is equal to half of the inductance multiplied by the current square. So if there is no current, there is no magnetic energy, and so I cannot talk about inductance, and vice versa. So we need to have magnetic flux or magnetic energy somewhere, and the coil somewhere else to talk about inductance actually. Yep. So let me talk once again on the magnetic energy. but now on the variation of the magnetic energy. When we vary the magnetic energy, we are going to create a magnetic force, right? So this magnetic force, it will be always attractive. Okay, so uh, if you see on the stator on the rotor, the magnetic energy on the rotor will create a force that will attract the stator, and in the stator as well, the magnetic energy variation will create a force attracting the rotor to it. So the magnetic force is created by the variation of the magnetic energy. We're going to see later another kind of forces called the Laplace force or Lorentz force. So this is really a difference uh, between electromagnetic world and the mechanical world. So mechanical world is a force is a force, and in magnetic world, where there is a split between magnetic force and Laplace force. Why? Because once again, the magnetic force is due to the magnetic energy variation, and it's always attractive. Whereas the magnetic or the Laplace force or Lorentz force, sorry, is depending on the orientation of the current actually. So this is something we have to keep in mind when we deal about the magnetic forces. Yeah, so then the magnetic forces is created by magnetic energy, and magnetic energy is concentrated in the air gap, and the variation of this magnetic energy on the air gap will create this magnetic force. So higher is the magnetic energy, higher is the force we are going to create. And then uh, the magnetic energy will create a force, and this force will tend to go always to the stability. So to have a stability and to maximize the magnetic flux. Then, if we maximize the magnetic flux, the system will tend to minimize this energy actually. So here, if we this electromagnet device, if we put this mobile piece on the top, when we supply this coil, we will create a magnetic energy variation, and then the force will tend to move this piece to the bottom, right? And then here, where we have the maximum max, actually, and then we minimize the energy. So if we minimize the energy, it means that we tend to eliminate the air gap actually. And this is the concept we want to use for rotating machine, because we are always uh, trying to create this magnetic energy variation on the stator, and always trying to maximize this magnetic energy. So if we take this device, which look like a front rotor synchronous machine, then if I will not, I will supply only the rotor, okay, and I will not supply the stator. So then, if I move the device, I will create what we call a cooking torque. So then, when the rotor pole is aligned on the stator tooth, this is where I have the maximum flux, and then this is where I have zero torque actually, right? So in this position, this is the stable, the balanced position. So or the stable position, sorry, where we maximize the magnetic flux and we minimize the energy. Then, if I move it with a given position, then I will feel that there is torque. Then the movement will create the magnetic energy variation, and then will create the force and then the torque. Same thing if I supply the tooth on the stator, and I will not supply the rotor. In this case, I will feel the same thing. If I move the rotor, I will feel this torque that tends to move the rotor in the opposite position in order to stabilize it, minimize the magnetic energy. So this is at the end of the day, this is what we want to do with Park model. So we try always to supply the stator, and we try always to know the position of the rotor in order to have always this angle between the stator and the magnetic field produced on the rotor. And then we try always to maximize that torque. Yeah, so then when there is this magnetic energy variation, we are going to create the force and we are going to create the torque. This is another example where when we supply the coil and this bar, there will be attractive force in order to maximize the flux and to minimize the magnetic energy, right? So this is always a matter of equilibrium, a stable position, and minimizing of magnetic energy and maximizing the magnetic flux. What I want to keep in mind actually is that magnetic force is always attractive, and we want to use that behavior in order to maximize always the torque in a rotating machine. Okay, so let's talk a little bit on Laplace force or Lorentz force, depending where you are. I'm based in France, and I like to talk or use Laplace force instead of Lorentz force. Sorry. Yeah. So then Laplace force, what is it? Here, if we use Laplace rail in order to understand this phenomena, so we will take like two bars, right, in parallel, fixed, that we are going to supply, and a bar which is moving. It's not fixed. This bar can conduct the current from this bar to the other one, right? The current will be moving like will have the U shape. Then the mobile bar is inside the magnetic field produced by these two magnets, so north, south, uh, and then once we supply uh, this system, uh, we are going to see a, a, in this bar magnetic force, and this bar will move because it's not fixed. What does it mean here? It means that Laplace force will be depending on the current, the orientation of the current I am going to inject. If I inject it in the other side, it will move, the bar will move in the opposite side, not like the magnetic force actually. So the principle of the Laplace force is that a given conductor inside a magnetic field, when it is applied, a Laplace force will appear on it. And this Laplace force orientation will depend on the current orientation. Okay. So Laplace force is something we use for DC current machine. We can use it like this reader on the hard disk, where you have the heat reader here, which is and this is a coil, and we have here two magnets. Then when we supply the coil, you will see Laplace force appearing to move the reader in this direction. I will inverse the current, it will move it to the other direction, and so on. The other one example using Laplace force principle is the voice coil. Here we have the magnet, and gray one is a magnetic circuit, and then you have the moving moving coil fixed with the membrane that it will move. And when I supply this coil, you can see that B is like this in this direction in the red law, which is the magnetic flux. And then the current is from you to the screen, and then we will see movement of the coil on Y direction, right? So if I vary the current amplitude or the current orientation, then this coil will move, can make move linearly on y axis. Okay, so this Laplace force for a synchronous reluctance machine, this is something we are not going to see for BLTC as well. But this Laplace force can appear actually on the windings, or it can appear as well on the bars where you induced the current, right? So let's talk particularly on this Laplace force on winding. So if you have the wires that can move inside your slot, when you supply your machine, there is a leakage magnetic flux. So if I plot the starter slot like this, and you have the wires, when you supply actually your coil, there is always this canalized magnetic flux actually, but there is as well some leakage magnetic flux inside the slot. So there is leakage magnetic flux, there is the current on the wires, so there, we will have Laplace force. If they have degree of freedom to move, then they will move actually, and they can go out to the slot. If they cannot go out to the slot, the movement, if there is two, let's say if you have the wires in touch and they will touch between them, it will degrade the insulation, and at the end you may have like accelerate the short circuit, the turn short circuit, for instance. So this is something important to have in mind, and this is why we have actually we try to fix as much as possible wires in the slots. Yep, let's talk now about the electrical load. The electrical load is mainly talking about voltages. So if I consider the same torus, simple example we had previously, then the voltage on the two terminals of this coil is equal to the resistance multiplied by the current, the resistance of the coil, and the current supply, plus dphi by dt. Actually, dphi by dt, if you remember, from Faraday's law, is a voltage actually. So if there is a magnetic flux variation across the time, we are going to create a voltage as well. So if we supply with a DC current, there is no magnetic flux variation. But if we supply with this voltage, then the magnetic flux variation will create a small voltage, and then when the current is continuous, this voltage will be 0. But if you have AC current, then this equation is always true. And this is what we are going to use for rotating machine because dphi by dt is always there. Because there is always a magnetic flux variation due to the AC supply and due to the rotor position, actually, especially if you have a magnet on the rotor. Okay, so this is what we are going to use later on to build a matrix of voltages and then move to Park model. Okay, so once again, R is the resistance of the coil. Phi B is the magnetic flux seen by the coil. And then it's logical to say that dphi by dt is the voltage induced on the coil due to the magnetic flux variation. So we talked about the inductance previously. We said that it's linked to magnetic energy, but the inductance can be simply phi by E actually. And then let's see how we can build the matrix of voltages of a circuit of a three-phase machine. But let's start by simply two coils. So we have coil 1 in front of coil 2. If I supply coil 1 by I1, I will produce a main magnetic flux. And I will have this blue magnetic flux, which is the leakage magnetic flux. So the inductance of this coil is Vp, the principal magnetic flux, divided by the current supply. Then this is only if I supply coil 1, right? And then this principal magnetic flux is equal to the main magnetic flux I created and leakage magnetic flux. So why I am talking about main magnetic flux? Because there is a second coil in front of it. So I am going to induce magnetic flux variation. It's same thing if I produce magnetic flux on the stator, and this magnetic flux will move from the stator through the air gap to the rotor. So this is the main magnetic flux I produced, and we have always, unfortunately, this leakage magnetic flux. So then we have this inductance, self-inductance, which is equal to the magnetization inductance, then Lm plus the leakage magnetic flux for the coil 1. Then there is concept of mutual. The mutual is, again, if I supply only coil 1 and coil 2 will see magnetic flux, the main magnetic flux created by coil 1 in coil 2. And this is what we call the mutual inductance, and it will create the mutual inductance. So then there is the principal magnetic flux created by coil 1. And then if I supply the coil 2, I will create as well the principal magnetic flux. And then we will have this mutual inductance between coil 1 and coil 2. Okay, so if we supply coil 1 and coil 2, we can easily create two equations depending on the mutuals and the self-inductance of each coil. Here, if I supply coil 1, then I can say that it's depending on it's in self-inductance plus the mutual inductance due to the coil 2. If in the coil 2 I have zero current, then the coil 1 will have only magnetic flux created by itself, and then it will be depending on the self-inductance of it. Once I supply the coil 2, I will have this mutual inductance created, and then it will be added then on the flux created by the two seen by coil 1 and created by the two coils. So this is for coil 1, and coil 2 is similar, and then we can create this matrix. So Phi1 created and seen by coil 1 is equal to its self-inductance multiplied by the current supply of coil 1 plus the mutual inductance multiplied by the current going through the coil 2. The magnetic flux on coil 2 created and seen by coil 2 is equal to the mutual inductance multiplied by the current supply on coil 1 plus its self-inductance of the coil 2 multiplied by the current going through into the coil 2. So this is for two coils. We can say that this is for two phases. We can say, if we add a third one, three phases, then we will have a matrix of three lines, right? Then same thing. It will be depending on its self-inductance plus the mutual between the considered phase and the other phases. Why I am talking about magnetic flux mainly because the resistance is something we know rapidly, and then I need to characterize this voltage due to the magnetic flux variation. So to build then for each phase of the stator, VA, VB, and VC, it's equal for its resistance multiplied by its current plus dphi A by dt. And we need to know how to write this phi A, and phi A, then we have this matrix. It's depending on its own inductance plus the mutual inductance between phi A and phi B and phi C. If there is coils on the rotor, it's more complicated. Then the matrix will be bigger, right? So you have the magnetic flux on phase A, phase B, phase C of the stator, and the same three phases on the rotor, and then the mutual between the phases of the stator and the mutual between the phases on the rotor, and the mutual between the stator and the rotor. So we will have this big matrix, and one can understand why we move from this three-phase system to Park model with DQ, only DQ axes. For synchronous machine, permanent machine, we don't have this one on the rotor. Then the matrix is smaller, but it's still more complex to manage than only two axes. Okay, so this flux is depending in the case of rotating machine, it will be depending on the mutual on the stator. This mutual on the stator will be fixed. The mutual between the rotor coils will be fixed, but the mutual between the rotor phases and the mutual and the stator phases will be varying, and it will depend on the rotor position. So that's why we have this reluctance variation or inductance variation due to the rotor position. And that's why for each working point, we need a given control angle in order to maximize the torque, because this mutual inductance is varying according to the rotor position. Okay, I am done for the first module. Let me see if you have question, and if you don't have question, we can have a break of 10 minutes and then come back to the second session. If you don't have question, then I am going to stop for the moment sharing, and let's come back in, uh, in 10 minutes. Okay, so we come back at 4 and 4:50. No, 4:15. Sorry. See you later. Again, uh, let me share my screen again. Okay, so let's go to the second module now. Yeah, so before going to the link between flex motor and synchronous reluctance machine, in this module we will start talking about the different link you can have. But before that, let's talk about a little bit about the different families we have. There are a lot of classification of motors, but this is something we tried to put here, depending on the principle of its machine. So our focus is actually mainly on this family. So where we have magnetic field on the rotor and magnetic field on the stator, and then there is uh, here the interaction between the stator and the rotor. And there is another principle is the reluctance variation. So uh, mainly switch reluctance machine, there is only a magnetic field on the stator, and the rotor there is no magnetic field. So only we play on this reluctance variation to create a movement. And then there is another family based on Laplace force principle, which is mainly DC motor, right? The synchronous reluctance machine is an hybridization between uh, this AC magnetic field machine and the reluctance variation family, because there is no magnetic field on the rotor, and the stator is supplied with AC current, whereas the switch reluctance machine we supply with a pulse of current depending on the rotor position. So the two main big families, there is synchronous machine, which is already larger than the family of the induction machine. And even between those two families, there is hybridization, right? So we can find like line start machine. So for synchronous machine, you have like a hydro generator where it's a wound rotor synchronous machine. They are very big machine. You can find like a claw pole machine, axial flux machine, and the well-known permanent magnet machine. And once again, there is as well the synchronous reluctance machine and what we can call synchronous reluctance machine assisted by permanent magnet. And here in induction machine, you will have a squirrel cage induction machine, wound rotor induction machine, massive rotor induction machine, and single phase induction machine. It can be like ring short circuit like this, or with two phases plus the capacitor. Yeah, so there are a lot of technologies actually, and if we classify them by families of principle, we can really see these three big families actually. And if there are a lot of machines, so there are a lot of application, and then we'll see on when we are going to design the machine, we are going to talk that to see that a given machine is designed according to its application. So there are application, mostly industrial part, where we have this induction machine, synchronous machine. They are used on generators, transportation. A DC machine, again, they are used on industry and then transportation as well. Switch electronics machine, mainly on uh, precision equipment where we need to move by a few angles and not rotation like high speed rotation, like a robot, for instance. Yeah, so then depending on the application, we can choose one machine that can be better than the other one. Yeah, concerning our machine today, as I told you, it's called synchronous reluctance machine, and the stator is exactly like a permanent synchronous machine, permanent magnet synchronous machine, where we have three phase, and it's exactly the same kind of stator and winding. But the rotor, there are really plenty of configuration. Um, I will focus mainly on those configuration, radial lamination and axial lamination. As you can see, understand here that radial lamination, they are laminated like this, and you can find the bridges. Um, where axial lamination, they are cutted like this, and actually there is no bridges inside, and we need like maybe something mechanical fixation, like we do have here with a screw or a sleeve or something like this. Yeah, in flex motor anyway, we do have only this kind of lamination, but there are other kind of rotor used for synchronous reluctance machine, not available in flex motor. So I will not talk about them, but yeah, you can see massive rotor, segmented rotor, uh, rotor assisted by magnet. They are actually between a full permanent magnet machine and a synchronous reluctance machine because we use ferrite magnet inside, and the control command is different from the permanent magnet machine because we'll see the part model of synchronous reluctance machine is really different from the one. Uh, Actually, it is the same, but the angle or the control angle is not in the same location. Yep. So once again, there are some hybridation. We can find like a squirrel cage even for synchronous reluctance machine. So it is like a kind of line start machine. So it starts directly on the network, and then once we reach it, the speed close to the synchronous, the stator magnetic field rotation, it will then catch this magnetic field rotation on the stator, and it will become like running like a synchronous machine. This is not something we have in flex motor. So what we have in flex motor so far is uh, the same stator and these both case of kind of lamination. So what is the principle now of this machine? We said that when you supply the stator are going to create a rotating magnetic field on the stator. Yeah, so this magnetic field rotation on the stator will be really quick, depending if you put it on the network directly, it will start directly at 50 hertz. and 50 hertz is speed much more fast than will not allow the rotor to catch it. So that's why even for synchronous reluctance machine, we need to start the magnetic field the stator with slower frequency and going faster and faster. Why? To allow rotor to catch up the magnetic field on the stator. So how this will be possible, because there is no magnet on the rotor. Yeah, so then this is possible because this magnetic field created on the stator will magnetize the rotor, and then it will create on it polarity north and south. Yeah, so then if then we start with a smaller uh, frequency, so we start slowly to start with small frequency on the stator. So then the magnetic field will rotate slowly. So then we can fight against the inertia of the rotor, and the north created by the magnetic field supply created on the stator will create this polarity on the rotor, and then since we are moving slowly, the rotor has the time to catch up. The north of the rotor have the time to catch the south of the stator, and then it will move like this. Okay, so if it will move with it, it will move with the same speed. Then it will be a synchronous machine. And since there is a reluctance on uh, the rotor, it is a synchronous reluctance machine. And this is exactly the same thing for switch reluctance machine, where uh, we supply each time the tooth in order to attract uh, the tooth on the rotor. So it's the same principle here. Then we are going to talk about this control angle. Why? Because if you remember, we said that if the rotor is aligned on the magnetic field of the stator, so this is where we have maximum magnetic flux and the minimum energy, and then minimum force or zero force, and then zero torque. So then more you have this angle between the axis of the stator magnetic field and the axis of the rotor, more you have torque. Then what we try to do is to put a sensor on the rotor in order to know its position at each time. And then we are going to supply the stator in order to put always a given angle between the rotor and the stator in order to create and to maximize the torque for a given current supply. Okay, so this is it, and it will really behave like a synchronous machine, uh, but there is no magnet on the rotor. Okay, so we have to keep in mind as well that it always this maximizing magnetic flux, minimizing the magnetic energy in order to create a stable system. So here, when we have like like 90-degree angle between the magnetic field on the stator and on the rotor, the axis rotor, this is where we maximize maximize the torque. Sorry, here it's 45 and it's not 90-degree. And where we have the stator aligned magnetic field of the stator aligned with the rotor axis. This is the stable position. So if we move it like this, it will come back to the initial position. If we move it to the other position, it will go back to the initial position. Here, if we move it in one direction on the other direction, it will directly go in this direction or in the opposite direction. Here as well, it's a balanced position where if you move it one direction or on the other direction, it will come back to its initial position. But we have zero torque in both position. And once again, here where we try to have the maximum torque. Actually, what we plot here is what we call a reluctant torque, and this is once again the reluctant, the origin of the name of synchronous reluctance machine. In a permanent magnet machine, we used to have the maximum if there is no reluctance variation. Surface permanent magnet machine, the maximum torque is obtained at 90 degrees. And here, since we don't have magnet and we have only the reluctance and we are going to play on this reluctance, then as you can see, the maximum is not at 90 degrees, but it's somewhere between minus 70 and 60, minus 60. So this is exactly what we call a reluctant torque, and this is the interaction of between the magnetic field on the stator and the reluctance variation on the rotor. We can see the same thing on the permanent magnet machine on the cogging torque, which is the interaction between the magnet and the reluctance variation due to the stator slot. Okay, so when we are going to control the synchronous reluctance machine, we are going to look to the maximum value or the angle to have the maximum torque. Yep, so since it's a synchronous machine, then it's the same principle for the speed. So the mechanical speed is equal to the synchronous, the mechanical speed is equal to the electrical speed if the number of pair poles is equal to 1. Yeah, so this is the relation that make a link between electrical quantities and mechanical quantities. So the mechanical speed here is equal to the electrical speed divided by the number of pair poles. And once again, here the synchronous speed is 60 by f. F is the frequency by the number of pair poles. Here is the phasor diagram. If I move, we'll see at the end the park model, but let's see here if we move from the three-phase matrix to only DQ representation of the machine. So here V is the voltage supply, I is the current supply, then there is no back EMF, right? So back EMF is not here like we do have for the due to the magnet on the rotor, but there is a back EMF due to the inductance variation, and the inductance variation is here due to XD and LD and LQ, which is this is a voltage created by the reluctance variation. So this is the main difference between synchronous reluctance machine and permanent magnet machine, where the control angle is really only on this quadrant. But here for synchronous reluctance machine, the control angle C, which is always in this quadrant. Okay, once again, the torque here is only a reluctant torque. There is no, I take a picture. Actually, for a permanent magnet machine, we used to say that a torque produced is this one. If we produce a torque between the interaction of the magnets and sorry. If we have only the winding on the stator and the magnets on the rotor, we are going to produce this torque. Okay, and if there is inner magnet, so inserted magnet, we will have what we call reluctance torque, which is the interaction between the magnetic field on the stator and the magnetic field on, the reluctance on the rotor. And we will have what we call Cogging torque, which is the interaction between the magnets and the stator slots. Here, for synchronous reluctance machine, there is no magnets on the rotor, so this torque is not produced. There is no magnets on the rotor, so this torque is not produced at all. So remain only the reluctant torque, and this is where we try to maximize the reluctant torque due to the reluctance of on the rotor. So if you have a disc on the rotor, it will not work. Okay, so this is the aim of this view. So this is this part of this equation is to say to make the interaction between the magnetic field produced by the magnets and the magnetic field produced by the winding. Since there is no magnet, so this part is equal to 0, remaining only this part due to the reluctance. The synchronous reluctance machine has its own limit, like for a permanent magnet machine. So it has the same limit like the power supply. You cannot, if you have a power supply of 30 kilowatt, you cannot produce a torque that going more than 30 kilowatts. So you will, if you have a supply of 30 kilowatts, you will produce maximum will be to 30 kilowatts in really ideal way. The other limit is the natural stability. We said that we have to avoid the breakdown. So we cannot apply a given load for a given, more than a given load for a given current supply. And then the current supply, this is the other limit then, because your power electronics, if it supply a maximum of 100 amps, you cannot ask the machine to run at 200 amps, for instance. Okay, so these are the limits we have for synchronous reluctance machine. Then, what about flux motor? Flux motor cover for the moment 3 technologies of motors: permanent magnet machine, inner rotor, outer rotor, induction machine, inner rotor, outer rotor, and then synchronous reluctance machine, inner rotor only, because they are the most used one. we don't have seen a lot of them as outdoor rotor. It can be possible anyway. And in flex motor, so far, all the machine we have, there are three phases. Okay, so then if you follow the introduction training within flex motor, you will see that you start with the supervisor, which is this one. And then you have motor catalog, okay? Uh, Motor catalog where you can create your own project depending on specification you have. Part library where you have several parts for magnets, for synchronous machine or synchronous reluctance machine. You have material library. You have few materials available directly in flex motor, but you can create your own motor. There is a script factory if you are familiar with the Python, so you can really drive flex motor through Python scripting. It's something really helpful to make some parametric computation directly through the scripting. Or maybe if you want to drive flex motor and to put flex motor in optimal or multiphasic computation. Yeah, of course, there is a part as most of Altair solution, the units and the preferences that you want to do. And there is a help and documentation. So the help, there is a PDF directly available. There are some interesting PDF to read. There is a support, the team where I am, where we can help. If you can write through your Altair One account to us, so we will be happy to help you. There is a forum as well. So the forum is a public, so all the questions you are going to say or to ask, they are public. So be careful to not share their confidential project because they are public. If there is some confidential project, I advise you to write us directly to the support. So only the team and you will have access to this file. And if there are issues, then the R&D team will be asked for help. Yeah, and there is knowledge-based articles available from Altair community and some videos as well. Do not hesitate to have a look on them. And then once for a given project, once you have your own part and your own material, then you can start to create your motor in the catalog you have already created. So the journey in flex motor, I advise you to always start from motor catalog. So you create your own project. So motor catalog is here. Then once you create your motor catalog, if it's first design, I believe that the few materials we have available can already help, as well as the few part we have. They are also helpful, or maybe it's better to start with existing part before going to more complex one. Yeah, otherwise you have to create your own material, from materials library, and your own part for part library. Okay, so then once you have created your catalog, then in your catalog you can create your synchronous reluctance machine. Here, for instance, I created this catalog for our example. Then you can use this catalog and put one candidate or all the iteration you may have for a given project. And then here you can start a new motor. And when you start a new motor, yeah, for sure you will start from design. Then the design it will be I will start a new motor here. We'll call it demo. And let me put the date. Okay, so here you will have flex motor philosophy is really easy to understand. Let's start from the top to the bottom for this part, design, test, and export. Then the design is from the left to the right, and you will start from the topology. And you will see that Flax Motor will ask you always a starting general dimensions, mainly the number of poles, the number of slots, and yeah, the diameters, the air gap to start. And these are the main points to compute before before going there. Then you have the shape of the rotor that you can uh, select from already a lot of shape here. As you can see, there is a radial and axial lamination. Then once you finish the rotor, which is really not obvious, totally not obvious to select the right shape, we are going to see some indication to help us to choose the right number of layers and the right shape to consider for our computation. Same thing for the slot. The slot is more easier for us to manage. Then the winding, which is really in Flax Motor, has a really helpful tool depending on the number of poles and the number of slots. Flex Motor will be able to propose you different configuration. So it's up to you to test the different configuration and then see the spatial MMF, what we were talking about when talking about the Ampere's law. Then this MMF, it should be sinusoidal and with a low number of harmonics. So depending on the configuration, possible configuration you select here, you have to look on the fundamental on the harmonic distortion, total harmonic distortion. Then the number of wires, the number of turns, end winding, and so on and so on. And then the materials. You can see that there are cooling, strategy, and housing and shaft. This is only interesting if you deal with the thermal computation, but for at the moment for the magnetic, yeah, topology, silences, slot, and so on are okay. Then you have to select the materials, the lamination for the stator and the rotor, and generally we use copper for the winding, and it's done. Okay, then you have test, model test to export the tables, lookup tables for system analysis. Thermal test, it's mandatory to do it, but for the moment I am not going to talk about it. Sine wave test is really interesting to start with because you will have the saturation, and the saturation play a big role here for synchronous reluctance machine. So we'll try to manage location, especially on the flux barrier, to reduce the saturation on them. And this is the test, the only test where you have this ISO value, ICN test. Okay. Then the efficiency map at the end of the day, this is what you want to do. And if you have a duty cycle, you can put it on it. This is important test as well because you will see the maximum performances of your machine. And then the last test available is the NVH. So NVH test here is really helpful in order to choose one candidate because you can have 2, 3 candidates. Magnetic and thermal are okay, but which one is noisy? This is something you can choose directly and compare through the mechanics. Then you have export. Can export the report. Report is really useful because you have possibility to put all the inputs and the tests you have already done, and it will generate this PDF report. The script factory can generate a script of your project that you can reuse in script factory. HyperStudy, this is as well useful link in order to make some design of experiment or some optimization with the help of HyperStudy. So HyperStudy will drive your project, your flex motor project, and you are going to select the parameters that HyperStudy will drive and the outputs that you want to have from flex motor, and you are mainly done actually, and then all the rest or the remaining part is will be done in HyperStudy. There are some advanced analysis that we don't have directly in flex motor. That's why you need to move to FlexStudy to make like eccentricities or short circuit analysis or to take into account some additional losses with the PWM supply, for instance, that you can't take into account within flex motor, for instance. Yeah, so the flex motor is really helpful for the pre-design stage, and our example at the last session will be done mainly with flex motor. So we'll see how to use flex motor to design then a synchronous reluctance machine from scratch. Okay. Yeah, I want to come back then to the assumption. Flex motor is really a mix between analytical and finite element computation. So finite element computation are mainly magnetostatic computation in order to take into account the saturation and well take into account the non-linearities of the material. Then we use these magnetic flags to compute the different inductances and then build the park model as well. So this is to have a good ratio between accuracy and time computation. Right. So the finite element computation are done behind, and they are invisible from the user. So you are not dealing about the mesh and so on. And the limits of this mix, analytical and finite element computation, is really due to the limit of Park, because Park model is applied with fundamental only. So the sinus, the shape of the supply is mandatory to be a sinus shape, and then the saturation as well, because Park model is not taking into account saturation. So if there are saturation, there are harmonics. So then there is it may have distortion on the result. Something also that we don't take into account directly in the efficiency map, for instance, the iron losses on the rotor are neglected. the joule losses on the magnets for the permanent magnet machine are neglected as well on the rotor. But there are some tests in flux motor. When you see, for instance, this test, and there is FAST, which is using Park model and magnetostatic computation, and accurate. When you see accurate, it's the full flux study, full finite element computation behind. Okay. All right. So let me go back here. And we are done for this module. I don't know if you have question so far. Let me go to the chat. Yeah, if you don't have question, we'll continue the third module, which is magnetic materials. Okay, so let's have a break of 5 minutes and come back again and to have this to discuss about magnetic materials and what is used in flex motor, and let's understand a little bit on iron losses and the eddy current losses as well. Yeah, see you in 5 minutes. Again, let's come back and continue on the material. Let me share my screen. I think you can see my screen now. Okay, and let me put the chat here if you have a question so I can see them. Okay, so in Flex Motor, we do have this materials library. Let me open the here, and then if I go to material library, we do have few materials for the lamination, uh, for the magnets, and then for the insulation, as well as for the massive part like the shaft and the housing. So these materials, few materials for the lamination are here, but yeah, if you have the characteristics that we need for mechanics, because we are going to make some NVH analysis, for magnetic, mainly the BH curve and the losses, measure the losses um, for Bertotti model to extract the Bertotti model and the different component. So mainly the coefficient of the Bertotti model and the thermal characteristics, uh, thermal conductivity of this motor lamination. Then you can create it directly here. So in Flex Motor, we are going to use a Bertotti model. And before talking about Bertotti model, let's talk about the lamination. So the lamination, once again, we have few of them there, and you can create your own material. Just to say that if you say look to the meaning of this name M235 35A, it means that you have like 2.35 watt per kilogram at measured at 1.5 Tesla and 50 hertz. The thickness is 0.35 millimeter. So if I took the other one, M330, maybe M350, 50A, yeah, it means that I have 3.5 watt per kilogram of losses measured at 1.5 Tesla at and 50 hertz, and the thickness is 0.5 millimeter. So to create a new lamination, once again, is in the user lamination, and you can create your own lamination, but you need to have uh, the material characteristics. So if I make new and I will call it demo today of okay, then the mechanics, I do have the characteristics, magnetics. If I have the coefficient, it's good, or I can have the spleen curve directly that I can go to select the file of the pH curve I have, and then I can import it, and then make a fit of this pH curve to have a optical model. You can modify it a little bit if you want, if you are not happy with the fit. Then, okay. Same thing, something you have to know that the material you imported is blue one, and depending on the stacking factor you used, flex motor will use the dark one because it takes into account the impact of the lamination on the initial pH curve you have. So if you had measured on a ring, on a solid one, so this is good. But if you have measured the pH characteristics on Epstein square, then you have to be careful because the lamination are already the lamination impact are already taken into account. Yeah, something for the iron losses. If you have the coefficient of the Bertotti model, it's okay. It's never the case actually. Then you need to have the measurement. So the measurement here, uh, you have the file uh, like here, where actually you have the data for different frequencies. Here we do have 50 hertz until 700 hertz. Okay, but you can have the measurement for a single point or 2 points. But ideally is really to have a measurement for different frequencies, the highest frequency possible, and the highest flux density possible as well. Then the fitting will be done, and you are okay with that. Yeah, so this is for the lamination, and the Bertotti model actually has these components. So U1 is the total. Then there is a hysteresis losses, classical losses, and excess losses. This is what we are going to see today to understand or the meaning of each part. Okay, then you have a solid, in addition of the lamination, you have a solid part, mainly for the housing and the shaft. Once again, we are not taking into account the eddy current inside the rotor. But if there is a massive part, you need to create a material corresponding to this massive part in order to use it in your computation. Because in one hand, there is no iron losses on it, only eddy current losses, and hysteresis losses as well. But that the model will not be applied. In the other part, there is this impact of the lamination on the pH curve. So, and normally and often the solid pH curve is really bad compared to the pH curve of the lamination. I'm not going to talk about the magnet behavior, but I put it here because I think it's helpful for those that will deal with permanent magnet machine. So since there is no magnet, I will talk only on the lamination and the hysteresis cycle and what we call intrinsic curve. So what happens really when we talk about the pH curve and the magnetization of the lamination? So let's start from this microscopic view of the lamination. So in detail, the lamination are a given number of what we call crystal, and inside it there is a block with what we call a domain that having a given orientation of their magnetization. So when we apply an external magnetic field on this lamination, the one having the same orientation like the external magnetic field will be larger and larger. So it means that we start to align all the magnetic moment in the same direction with the external magnetic field. So we start to, by increasing the magnetic field, we increase the flux density on it, we increase the magnetization on it, until all the domain are oriented in the same direction. Then we start to saturate the material. So actually, this is what we call the first magnetization curve. There is this first knee and this second knee. Then when we saturate and we start to decrease the magnetic field, we will not come back in the same way, in the same path, but we will go back with hysteresis, what we call a hysteresis effect. Then when we have zero magnetic field, then we still have a remanent flux density. So we magnetize the iron. Then if we reverse the orientation, then we start to demagnetize the iron until having zero flux density on it. We continue to add more magnetic field in the opposite direction. We magnetize the material in the other direction. Then we saturate the material, and then we come back in the other path until having zero magnetic field, and then we will have again remanent flux density on it. So we magnetize once again the material, and then if you put opposite direction and you start to add the magnetic field, increase the magnetic field, we are going to magnetize it until reaching the saturation. So we will have this hysteresis loop. And actually, what we need for our computation, it's not the first magnetization curve, it's really the middle of the loop, which called intrinsic curve. And this is what we ask in flux and flux motor as a pH curve for our computation. Then this hysteresis loop will define two main families, right? So the one having a thin loop, which is soft material, mainly lamination, and the one having a large loop, it's hard material, mainly magnets, right? So this is something important to know. And the losses, the hysteresis losses are, this is some what we have on the loop actually. So thinner is the loop, better is our lamination. Yeah, something I wanted to add here about the domain here. It will we will define two families. There is oriented grain and non-oriented grain. So the oriented grain are mainly used for transformers, high power transformers, and non-oriented grain are used for rotating machine. And in this non-oriented grain as well as oriented grain, we will have the same behavior, right? So we will plot the same loop of hysteresis. Okay. Then I am going to continue on the lamination. So why are we laminating the stator and the rotor? This is in order to reduce the losses. We will see later on that the fact that we make the lamination, we will degrade a little bit the material characteristics, and since we are going to laminate, we will have what we call a stacking factor. So let's see how we degrade this initial magnetic pH curve due to the lamination. Once again, we make this lamination technique in order to reduce the eddy current inside. So let's consider given stator. Let me, so the stator will create a magnetic field like this, for instance, a 4-pole machine. So the magnetic field will move like this, and the lamination are like this. So finally, the magnetic field B is parallel to the lamination, right? So the lamination are parallel to B, and here, as you can see, between each lamination there is insulation. We can consider it as air. Why there is insulation? To avoid that the current go through the one lamination to the other one. So to cut the path of the eddy current inside the lamination. So then we will have an equivalent volume of iron and equivalent volume of insulation or air. And here, once again, B is parallel to the lamination. It's really important to know that. So since we do have the magnetic field source and we have iron and air, we can plot the equivalent magnetic circuit thanks to Hopkinson law. Then there is a reluctance of the iron, equivalent reluctance of the iron, and equivalent reluctance of the air, and they are in parallel. So then I have reluctance air and parallel with the reluctance air, like iron. I can compute, like for electric circuit, an equivalent reluctance. Then from this equivalent reluctance, I can compute an equivalent relative permeability. So this relative permeability is actually depending on the geometric parameters because the reluctance itself is depending on the geometric parameters of our lamination here. So if I make an example, I have an initial relative permeability with 2000, right? And then with a stacking factor here of 0.95. So stacking factor is the length of the equivalent iron divided of the real length of the device. So if I start with this relative permeability, due to this stacking or lamination, I will lose on the relative permeability to a little bit to have like 1940. So this is in case of I have lamination in parallel of B. If I have a lamination perpendicular to the magnetic field, this is really bad. What does it mean? It means that in my machine, instead of having a lamination like this, I will have a lamination like this, and so on. And actually, this is really bad because I will cut the path of the magnetic flux. So instead of having two reluctances in parallel, I will add a reluctance to the magnetic field. And then the same example where I start with 2000, then 2000 became like 33. This is really something we have to avoid to do for the lamination. So once again, the lamination are very good to reduce the eddy current losses. But unfortunately, we will lose a little bit on the magnetic characteristics, but we will see that the gain is much more than what we lost. Yeah, since I am talking about eddy current, so let's talk about this eddy current creation and the losses due to this eddy current. So eddy current in a given material with a given BH characteristics, magnetic characteristics, and a given electric resistivity, sigma. If we put it inside a variable magnetic field, this variable magnetic field will create a potential. If you remember, Faraday's law or Lorentz law. This potential, since there is electric resistivity, it will create what we call eddy current, and this eddy current will create themselves magnetic field in opposition to the main magnetic field, and this system will be stabilized, and we will have anyway this eddy current. Unfortunately, so eddy current are something we don't want to have inside the lamination, inside the magnet. But eddy current, this is something we want to have inside the induction machine. Otherwise, it will not run. Eddy current, this is something we want to have. Sorry, in induction heating, for instance, like for a home appliance or some industrial application. So it depends on where we consider eddy current. They can be something we want. They can be something we don't want. So eddy current will be depending on the frequency. So the frequency will create what we call a skin effect. And this skin effect is something we don't want, especially in the winding. Actually, in the coils, you will have copper wires. If you have a big diameter, then you are going to use uh, copper for nothing, because for high frequency you will have this skin effect. And unfortunately, there is another phenomena called the proximity effect. Finally, the same wires will have this eddy current like this, unfortunately, due to the proximity effect. And this proximity effect is due mainly as well to the eddy current are due to the proximity of the other wires and the frequency. But you can have as well eddy current due to the leakage magnetic field, right? So even this eddy leakage magnetic field, it will be a source of eddy current inside the wires. So this is why there is a twist technique, and this is why we prefer to use to split the wires in. If you have 10 turns, or maybe if you have 4 turns, sorry, it's better to use 10 wires in hand for 4 turns. So this is another area where we don't want to have eddy current. So once again, if the eddy current appears, if I have like electric resistivity, the BH curve, the magnetic characteristics, it can play a role on the skin effect or not. But anyway, if you have a massive block where you apply eddy current magnetic field variation with a given frequency, you will create for sure a magnetic potential E. And this magnetic potential E, since there is electric resistivity on this block of material, you will create eddy current on it. And then this eddy current on it, if we make an integral, this current density, it will create this eddy current. And this eddy current, as you can see, it will be depending on the dimension of the block, but also on the frequency and the electric resistivity of the supply. So this eddy current will create losses. Here the losses can be computed like this. So at the end of the development, we can see that the losses for the volume can be written as a factor. This is one factor of Berthotti losses. And actually, this is one part of Berthotti losses. If I come back to my model here, which are classical losses, right? So then this is one part of the losses on the block. Then if I choose now lamination technique, so the initial length of the block, I will divide it on a small lamination. Let's say I will put n lamination. Then I can replace the length of the block here by the length of the lamination, right? And then finally, the losses on each lamination is divided by the number of lamination. Sorry, the total losses will be divided by n squared. N, if you remember, is the number of lamination. So thinner is the lamination, better is the reduce of the eddy current. But thinner is the lamination will have a limit, mainly mechanical limit, because thinner lamination, it will be hard to manufacture, to assemble, and we are not sure that it will not be, there will not be deformation due to the mechanical magnetic forces. This is one point. And thinner lamination, you will have more insulation, then the stacking factor will be bigger. Then it will have an impact for sure on the pH curve. So there is a compromise to find according to the mechanical limit and the impact on the pH curve. So this is a really clearly where we can see the impact and the usefulness of the lamination. So this is one part of the iron losses. Then there is hysteresis losses. Hysteresis losses is something you can observe if we make a torus, a laminated torus, and then we say that we have neglected here, for instance, we can supply with 10 hertz and the torus is laminated. So we can say that we neglect the eddy current losses, but we will still observe these losses in the measurement if we deduce, of course, if we minus the Joule losses on the coil. So we will observe always these losses. And these losses is something we call hysteresis losses. And the hysteresis losses are mainly the area of the hysteresis loop, right? And so that's why I told you thinner is the loop, better is the lamination, because we reduce dramatically hysteresis losses on it. And actually, if we develop the Faraday's law in dphi by dt, and phi is b flux density multiplied by the section, and we know that from we can build the equivalent circuit, the equivalent magnetic circuit, and then we can compute the magnetic flux and so on. Then the development will bring us to this expression of the magnetic energy, which is the integral, actually, the integral of the loop directly. So this is the energy, and if we go to the power over a period, then we have the energy integral of this HB over a period. Then we have period is equal to the inverse of the period is equal to the frequency. Then we can bring some constant parameter in a coefficient KH. And finally, the end of the day, the hysteresis losses will be equal to KH, which is grouping all the constant parameter multiplied by the flux density and the frequency. So here, the hysteresis losses are mainly depending on the flux density and the frequency. And actually, the frequency, depending on the frequency we have, the loop will be more different. So you can see here several loops at 0.1 hertz, 50 hertz, and 200 hertz. So the 0.1 hertz, we can call it as a static hysteresis loop. And you can see the other one for 50 hertz and 200 hertz. Then, depending on the frequency, you will have given hysteresis losses. And depending on the flux density you created on the lamination, you will have as well a given hysteresis losses. So we have classical losses, which are due to the eddy current, and then hysteresis losses, and remaining on the Bertotti model, what we call additional losses that are not physical, one, mainly due to fitting model needs against measurement results. And they, in some cases, they are due to the error of the measurement, actually. So then we have these three parts of Bertotti model, and this is what we use to use in flux motor. There is another model called loss surface model developed by our partner laboratory, which is GE2 Lab. This is also based on the measurement. But yeah, so far in flux motor, this is what we use, and this is the end of this chapter, this module, and the end of this session. Thank you very much to stay until the end, guys. Yeah, I will be happy to answer a question if you have. Okay. Yeah, thank you very much, Ramin. And I think I have a question from Slavomir. I have already sent this morning. I hope that yeah, Oscar as well. Please, the other guys, do you have received already it? Or let me give you my email. So if you don't receive it, please send me an email. I will send you back this. Okay. Otherwise, if you don't have a question, let me. Yeah, I have a question from Mayur. What about the mechanical stress? How to check that? Suppose rotor is rotating with certain RPM. So how we check that? Yeah, the mechanical stress. This is something we don't bring directly inside flux motor, but this is something you can test with OptiStruct. This is another solution we have within Altair, or SimSolid as well. You can compute the mechanical stress on it. But yeah, in flux motor there is no mechanical stress, and this is why I didn't include it here. But you are right. This is when you go to optimize a motor, mechanical stress is really important because you can have, from magnetic point of view, a good motor, but from a mechanical point of view, it doesn't respect the stress on the bridges, for instance, of the rotor. Okay. Something you don't know maybe in Flax now we do have shape optimization, and the shape optimization there is we include on it a loop to study mechanical stress. So Uh, for the shape optimization, for instance, if you choose to reduce the torque ripple, the shape optimization will take into account the mechanical stress and the electromagnetic performances. All right. Other question, guys? Okay. If no, thanks once again to stay until now. I hope that I will see you tomorrow as well to continue um, initial design, winding MMF, and talk about Park. Yeah, George. It's not the mechanical losses. The mechanical losses are not. I don't know if we can compute them actually. This is something you measure. But the question before asked by Mayer is: do flex motor take into account the mechanical stress, the mechanical constraints? And flex motor is not taking into account the mechanical stress. The mechanical analysis we are doing is only in VH analysis. So the mechanical torque, it's possible to compute it, but you have to include the mechanical losses inside flex motor. If you don't have this input of the mechanical losses, yeah, flex motor will compute in only the electromagnetic torque. Okay, other question? Yeah, thank you very much. Once again, George, I don't know if it's possible to compute the mechanical losses because the mechanical losses are mainly in the bearing, and I think it's very hard to compute it. And there are friction losses as well, depending if you have, uh, depending on your rotor shape and so on. This is something I don't know if there is a software to compute it. Okay, guys, thank you very much. And see you tomorrow, I hope. Bye bye.